The recording. And okay, hi everyone. So we are very happy to have Nobuyuki Ishibashi, who will speak on the Fokker-Planck formalism for closed bosonic string. Thanks a lot, Nobuyuki, for agreeing to speak with us, especially given the time it is in Japan. And the floor is yours, so please, thanks.
Okay. Okay, I'm very happy to give a talk here at the Journal Club for SFT. And the title of my talk is the Fokker-Planck formalism for closed bosonic strings. Okay, what I'm going to talk about is, of course, about string field theory. And the amplitudes in string theory are expressed by Feynman diagrams, which are world sheets, and mathematically they are Riemann surfaces. And if you have a string field theory, these Feynman diagrams should be obtained by combining vertex and propagators like this figure. So if you have a string field theory, there should be a rule to decompose Riemann surfaces into vertex and propagator like this. And so the rule should be systematic. And in general, we need infinitely many vertices to do so. So the action should be like this. And nowadays, people are accustomed to using this kind of action with infinitely many terms using homotopy algebra methods. And so that's very good. But what I'm going to talk about is something different. I would like to find a way to make SFT as simple as this. So I would like to find some way to cut the surfaces to so that the SFT action is consists of kinetic term and the cubic string interaction. And so far, there exist essentially two known rules for doing that. And one is the light cone type theories, and the other is Witten type theories for open strings. And what I would like to seek to pursue in this talk is to find yet another rule to cut surfaces so that the action becomes simple as this. And of course, as you know, this light cone type vertex or Witten type vertex works well for bosonic strings, and there are SFTs for bosonic strings with this schematically this action. But of course, there's for superstrings there's a problem of spurious singularity, and we cannot have this kind of simple action. So these ideas does not work for superstrings naively. So anyway, so I'm not sure if what I'm gonna propose is works well for superstrings. But anyway, we start from the bosonic strings. And the idea is the following. Okay, a Riemann surface with genus G and the n boundaries, and with and G and n satisfy this inequality, admits a hyperbolic metric such that the boundaries are geodesics. And this hyperbolic means a constant curvature metric. Usually it R equals -2 or -1, depending on convention. And this hyperbolic metric was used to construct string field theory by these people already. And I'm strongly influenced by the works of these people. And but anyway, and if you have a hyperbolic metric, we call surface with hyperbolic metric the hyperbolic surface. For hyperbolic surface, it is known that any surface can be decomposed into pairs of pants whose boundaries are geodesics. And the pants, pairs of pants means this shape. So any surface with this condition has a hyperbolic metric on it. And you can, with this hyperbolic metric, you can decompose any surface into this fundamental shape, a pants. So this fact implies that, okay, you can decompose any surface into these pairs of pants. So that means we may be able to construct a string field theory using this fact. So, okay, so this pairs of pants looks quite like some vertex of strings with three strings coming in. And of course, we have, okay, so they are, okay, so then propagator should be like this. This is not a cylinder. It's a infinitesimally thin cylinder. So you may be able to find, okay, so any surface, any Riemann surface can be decomposed into this fundamental building block. So that means we may be able to construct a string field theory using this vertex and this propagator. And then, okay, we have only three string vertex and the propagator. So that means action should be like this. But, and okay, first of all, if you consider this kind of string field theory, then it's very, very unusual. It's not, it's quite different from what we are used to. First of all, the string fields. Okay, we have string fields, okay, something here. So they come with the length of the string. Okay, so the string fields should depend on the length of the string. And that means we have one extra variable to describe strings field. So it's not the usual situation. Another thing is that propagator is this just a line. I mean, an infinitely thin cylinder, infinitesimally thin cylinder. So that means kinetic terms are not will not be the something we are used to, like this phi q phi conventional kinetic term. So that means okay, if you construct this kind of string field theory, it's very unusual, and actually I have done it, but I am not quite sure how to deal with this. But anyway, let's go on and find out if we can get some simple action for string fields. And actually, this was done long time ago, and people found that this kind of action does not work. This was done by Tohoka and Gross. This was not published, but this work appears in review by Tohoka and Fong on string perturbation theory. And what they found out is like this. Okay, okay, we have a kinetic term and the three string vertex. That's okay, we know the propagator and the three string vertex, so we have automatically this action. Then let's first calculate the simplest amplitude from one of the simplest amplitude, maybe a one loop, 1 point amplitude. So the Feynman graph will be like this. And this is the shape of the worldsheet. But actually, if you decompose this one loop, 1 point Feynman diagram into pants, then you find that there are infinitely many ways to do that. Okay, so you have to dissect the surface along some circle on this surface. But there are many ways to take the circle. And one is like this, another is like this. Okay, this is a sort of, if you ignore this one, this is torus. So there are two independent cycles for the torus. And then there are many ways to wind around these two independent cycles. And so there are many complicated ways to wind around these independent cycles. And of course, these configurations are related by modular transformation of the torus. And so there are, if you fix some one surface, Feynman worldsheet, Riemann surface with boundary like this, then there are infinitely many ways to decompose it into a pair of pants. And they are related by modular transformations. And if you start from this action and calculate one loop, 1 point amplitude, all these diagrams contribute. And of course, from the modular invariance, all these graphs contributes the same quantity to the amplitude. So that means amplitude, one loop, 1 point amplitude should be infinity times this one. Infinity comes from the cardinal number of the modular orbit. And actually, most of the amplitudes diverge in the same way. So the idea to construct string field theory based on Pant's decomposition does not work. If you construct the action like this, it is obvious to it is straightforward to construct the action, but this action cannot reproduce the amplitudes. Almost all the amplitudes diverge. So we cannot construct the action. This is known for many years. And what I would like to do is to, we can take an alternative approach. We cannot construct the action. So we take another approach, which is called the Fokker-Planck formalism. Let me quickly review what Fokker-Planck formalism is. Suppose you have it's a conventional field theory, point particle field theory with the action, scalar field theory with the action S. Then, of course, your correlation function can be expressed like this. And you can express this theory by what is called Fokker-Planck formalism. And this correlation function can be expressed like this. In the Fokker-Planck formalism, you prepare the operators, phi hat for this phi variable, and its conjugate pi, and they satisfy this commutation relation. Notice that this x and y are d-dimensional. If you consider d-dimensional field theory, then x and y are d-dimensional vectors. And they are canonical conjugate. And you also prepare the bra and get sort of a vacuum state, which satisfy this one. And you prepare what is called Fokker-Planck Hamiltonian, which is, in this case, should be like this. And if you calculate this quantity and take this tau goes to infinity limit, then, you can show that this quantity coincides with this one. It is another way to express the correlation function. And here, the tau is the time which is introduced from outside. It is called a fictitious time. And this formalism appears in the context of stochastic quantization of field theory, conventional field theory. So we
I have a question.
Yes.
Can you compare this to usual operator quantization in quantum field theory?
Well,
Looks
yeah,
quite similar, but
a bit different because usual operator formalism, this time you use time time is one of the coordinates, right?
Right.
And we, in this formalism, we introduce fictitious time tau, which is which has nothing to do with the real time.
So these operators in this Hilbert space have nothing to do with the operators in Hilbert space.
Nothing to do. Yeah, right. That your comment is right. Yeah.
So this is just kind of somehow a bookkeeping device of a kind.
Yes. Another way to express the same thing, right? In a conventional.
Is it obvious that it works, or should we just take it on faith?
Oh well. Okay. You have to. Okay, actually, you can prove that if you take each Hamiltonian to be like this, you can prove. Okay, okay, this Hamiltonian, if you do some conjugate transformation, then this Hamiltonian becomes well more tractable form, and then you can prove that this one is equal to this one.
I guess it should be an identity somehow.
Yeah, identity, right?
Yeah. So okay. So we just take your word for it. Okay.
Yeah. Okay. One way it is like a supersymmetric quantum mechanics. You know, in a okay, the ground state of this Fokker-Planck Hamiltonian is actually has the form like this, e to the minus s actually. Yeah. So if you take tau goes to infinity limit, then a ground state dominates, and that will make this the probability is proportional to this one.
Okay.
Yeah. But okay, it's a bit complicated. So yeah, you can consult some book. But anyway, this is not so important here. This conventional one is not so important in my talk.
Okay.
And
sorry,
yeah,
I have another question. So
yeah.
Is there a simple interpretation for the correlator when tau is not sent to the critical value infinity, but it's just finite?
I don't think so. I'm not sure. I don't think in the conventional field theory case, I don't know. I don't think tau, when tau is finite, I don't think it has any meaning.
Okay, thanks.
Yeah. So okay, so we have a some new Hamiltonian, and you can of course transform this formalism to a path integral formalism. It's just a straightforward way. So it's and we call it the action as IFB. Then the correlation function. Okay, you just rewrite this this one by path integral formalism like this. And what I would like to show in this talk is that it is possible to construct an SFT for closed bosonic string based on the Pence decomposition via the Fokker-Planck formalism. And the IFP, the action is given like this. And here, something different from the previous slide is that I have to put in some auxiliary fields, lambda. And it's a bit complicated, but it looks complicated, but this action consists of kinetic terms and 3-string interaction terms. And the theory should be in the Fokker-Planck formalism. And actually, in the conventional field theory, it's just a rewriting. For FP formalism is just a rewriting of the conventional formalism. So in that case, in the conventional field theory, we have this action and also this Hamiltonian and this action. But as I will explain later, in the string field theory in our setup, this S phi is not well defined. Okay, so that's what I want to claim, want to show in this talk. And this is based on this paper. And I said that, okay, so usual action does not work, and we should go to Fokker-Planck formalism. And Fokker-Planck formalism, you may feel that Fokker-Planck formalism appeared out of nowhere, but actually, there's a background behind this proposal, and that's what is given in this picture. Okay, mathematicians were interested in calculating volumes of a moduli space of Riemann surfaces. And a mathematician called Mirzakhani discovered a recursion relation satisfied by the volume of the moduli space. And later, people realized that this recursion relation can be considered as a loop equation of a one matrix model in a 2 infinity critical point. These people showed that. And so this mathematical equation is a kind of loop, what is called loop equation of matrix model. And I had an experience in dealing with that kind of equation. A long time ago, people in a old non-critical string era, they derived loop equation for 2-3 critical point of the one matrix model. 2-3 critical point corresponds to C = 0 non-critical string theory. And these people derived loop equation, and they showed that this loop equation is equivalent to what well-known celebrated Virasoro constraints, so-called Virasoro constraints. And later, Kawai and I rewrite this loop equation into a string field theory of a non-critical string. And that string field theory was in Fokker-Planck formalism. And I had this experience. So actually, this recursion relation, Mirzakhani recursion relation, can be also written into a string field theory in Fokker-Planck formalism. And what I will like to do, talk about in this talk is the generalization of this recursion relation. I will show that this recursion relation, this is a relation between volumes of moduli space of Riemann surfaces, but you can generalize this relation to a recursion relation for off-shell amplitudes of closed bosonic strings. And once you have done that, then it is very straightforward. This is kind of, if you consider this as a kind of loop equation, it has this almost the same structure as the loop equation. So then you can it is straightforward you can turn this relation to a string field theory form using Fokker-Planck formalism. And unfortunately, this string field theory is not invariant and manifestly invariant under the BRST transformation on the worldsheet. So I should rewrite this into a BRST invariant form, introducing auxiliary field. And that's what, okay, so the action here is something I got eventually following this development.
Hello.
And okay.
Question.
Yeah.
So the middle one that you said, the Mirzakhani relation to the directly, is it supposed to be like some sort of a string field theory for like JT gravity plus minimal matter? Like a...
Yeah, I think so. Yeah. Yeah, you can consider like that. Yeah.
Okay.
Yeah.
Also,
but I haven't published it.
I see.
Yeah.
So it also like, is it supposed to be like this dilaton equation on this matrix model supposed to translate to Gauss-Dilaton theorem?
In this case?
Yeah, like say that like there's loop equation and there's also Dilaton equation, right?
Uh-huh.
So Dilaton equation is kind of looks like a Gauss-Dilaton theorem. So if I just like run through this and get a like SFD, is it supposed to be is it supposed to reduce the Gauss-Dilaton theorem in SFD?
Okay, I haven't considered it.
Okay. Yeah.
Thank you. Yeah. Okay, so what I'm gonna, in the rest of my talk, I will talk about all these development. So I start from this Mirzakhani recursion relation. This is mathematics. Then I will talk about you can generalize this recursion relation to the one for the off-shell amplitudes for closed string, bosonic strings. And then I will turn this one into a Fokker-Planck formalism SFT. And then I will explain the BRST invariant formulation. Okay, so is it okay to, are there any questions?
Yes, I mean, I actually have like a general question.
Yeah.
You are using this singular slit as your propagator, right?
Yes, yes.
Like when I consider this like a covering all moduli space, your vertex region is the whole moduli space. Am I correct?
I mean, it covers. Okay, the
no propagate. So, what I'm confused about is, okay, if vertex region is whole moduli space, this I mean this surface, this string field theory contains degenerating surface as well, right? The degenerating surface is described by the propagator. So how come we can call this a field theory?
I mean, first of all, degeneration corresponds to the limit where one of this L goes to 0.
Yes. So my confusion is that like if we are trying to write a string field theory, we will keep like a propagator to describe that degenerating behavior, right? Because otherwise, the basically string shrinks to a point and it will be very singular. But if I have a propagator, I have like a field theory where I have like states propagating. So I'm quite confused about this. Like if it is not a field theory, like this doesn't sound like a field theory about something else. So
okay. I admit that. I agree with that. Yeah, it's not. It doesn't look like usual string field theory. So it's some theory of something, some strings, and from which we can derive the string amplitudes. Some composite quantity from which we can derive string amplitudes.
Yeah, but say for example, I want to like compute like a mass renormalization or something. Then how would I do that?
Okay. Mass. Well, you can.
It's just an example, or like I say that I want to find like a fix some IR divergences, like say that I want to separate the modes like that is propagating in the propagator. In usual structure, I can do it very easily, right? I can say, oh, there's a vertex and like the degenerating behavior coming from the propagator, and that will be like basically it's going to be like in field theory. I don't know if there is like any type of like say that how I able to usual field theory formulation in this Fokker-Planck formalism.
Okay, okay. That kind of question I cannot answer. I think okay. What I can say is that the degeneration corresponds to L goes to 0 limit. So if you reinterpret that L goes to 0 limit as the sort of a long propagator limit.
a color.
then you can do the almost the same thing. But I haven't done that. But
Okay.
or for mass renormalization, then you can also consider. Well, I think you just what you should do is just to find the right pole for the external lines, right?
Yeah, that's correct. Like
Yeah.
I'm
So
quite confused because the string, the usual flat propagator gives you 1/L0, and the pole is clearly there, right? But when it goes to 0, like probably I won't get a pole. Instead, I will get like something worse, like some sort of like a branch singularity or something.
well, okay, you can actually study the L goes to 0 limit by actually using your result in your paper.
Yeah, but the catch is that I put like a certain cutoff in that answer, and it's not exact. Like actually there is like the subtlety that limit is kind of singular.
Okay, that I don't know. I'm sorry. Okay.
I can chat later.
Yeah.
So another question is that somehow the S and T channel diagrams aren't automatically included, right?
Yes, actually, yeah. Well, actually, you
Oh.
have to add to yeah.
Or there's just one. You're just gluing these two pairs of pants and you're integrating over, I don't know, a twist angle and some length, right?
Yeah.
And that should cover the whole moduli space.
Right.
So
well, actually, if you do that for this action, then you just overcount everything.
Well, see, I don't even know what, when you write down that action, I don't even know what you're talking about there. I don't know what that is, because I don't know what. Okay, so
okay, so
yeah, it's a little bit imprecise. I don't know what is that action. How is this K to glue these pairs of pants in exactly the way that you want to? You know, the K that I know.
K is just a
propagator is always
delta
a tube, right?
Yeah. In this case, it's just a delta function.
Yeah. Okay. And
okay.
but it should also integrate over the length of the curve, right? And the twist angle, right? So the length of the curve should be something analogous to the Schwinger parameter.
Yeah. Right.
Right. But that, if you do that full integration should cover the whole moduli space of the 4-point amplitude, right?
Well, actually, okay, if you do that naively, then it becomes infinite. So that in the Fokker-Planck formulation, you have to add you have to assign some weights to that integration. You have to.
Another question is, a related question is that it's clear that, say, the S channel degeneration corresponds to L3 goes to 0 when you do that gluing.
Yeah.
Where's the T channel degeneration then?
Well, then okay, this that corresponds to this this cycle goes to 0. Yeah,
but okay, but isn't that? But you have these vertices, right? So isn't that overcounting or?
Okay, okay, so we have in the Fokker-Planck formulation, you have also contribution from this one. So you don't just simply integrate over the length of this one and twist angle, but you also add the other channel contribution in a Fokker. Okay. So okay, this is just the this what you're talking about seems to be corresponding to naive way of constructing this action.
Well, really, I'm just thinking about constructing a 4-punctured sphere by gluing pairs of pants.
Mm-hmm.
And with the usual, I guess these Fenchel-Nielsen coordinates, and you should somehow integrate over the Fenchel-Nielsen coordinates, and I guess that integrates over the Teichmuller space, though.
Mm-hmm.
So somehow one has to get down to the moduli space. I'm not exactly sure of the details, but that's what I'm thinking. The motivation is you're just taking these pairs of pants, which should somehow correspond to string field theory vertices. But really, this is just mathematical question. You're just gluing pants and you're integrating over a twist angle and a length, and this should cover the moduli space, right?
Yeah, right.
So, but you only need one curve to do that, right? Or you could choose another curve, but you okay.
Well. Okay. So what I said is that if you do that naively, you get into trouble because the amplitude diverges. It overcounts the whole. Okay. If you do that, integrate over this length from 0 to infinity, that overcounts the moduli space. Actually,
it's
even
because
for
you're integrating over the Teichmuller space. Is that
Teichmuller? Yeah, right. Actually,
okay.
even this three
but
amplitude.
Then adding another curve is not going to make, and integrating over that one is not going to make it better, right? Or okay.
Yeah.
Okay,
So
I guess
what
you will explain, but somehow the intuition here is a little bit opaque to me. But
yeah. But
it's not clear here where how the S and T channel degenerations are consistently accounted for in this picture.
Okay, so yeah, but actually, what do I think what I will do is to add this one and the T channel one with some weight, and then the whole thing becomes just the correct answer.
Okay.
Okay. Are there any other questions? Okay, so
Sorry, I wrote the question in chat, but let me spell it out. So I'm not a physicist. I don't necessarily understand most of what's happening, but in this step, when you go from the loop equation to the superstring theory, in this FP formalism.
Superstring.
Yeah, sorry, the SFT theory in the FP formalism. Do you get some sort of vertex operator algebra in it, where you could have a conformal element that recovers these Virasoro constraints?
Well, I actually, Virasoro constraints.
Yeah, well, you know, loop equation you said is equivalent to the Virasoro constraints in the moduli space.
Yeah, well, Virasoro constraints appear can be derived by taking L goes to 0 limit of the all the external lines.
I guess what I'm asking is if there is this algebraic structure called the vertex operator algebra, which contains a conformal element out of which the Virasoro constraints can be recovered.
Okay. I'll come to that later.
Okay. Thank you.
Okay, let me go on to the Mirzakhani recursion. And this is a mathematics. Okay, I'll start by explaining this Mirzakhani recursion. And this is mathematics, so maybe you can consult, if you are interested in it, you can consult the reviews here. So this is a relation of the volume of the modular space of Riemann surfaces with genus G and N boundaries. And we always assume the hyperbolic metric on it. And so we specify the length of the N boundaries to be like this. Then volume is given by this integral. And this measure is given by this. Okay, so this there are two these variables which parameterize the modular space of Riemann surfaces. This is the length and the twist angle, as Ted mentioned in his question. And so L is the, okay, if you can't decompose the surface, then L is the length of the non-peripheral boundary of the pants. And the theta is the twist angle to identify these two boundaries. And these variables parameterize the modular space. And the measure, the Veilleux-Peterson measure, what is called Veilleux-Peterson measure, is given, can be written like this. And of course, if you integrate it, this LS is the length of the loop. From 0 to infinity, the integral diverges. The reason is as I explained in the previous some previous slide, it is the pants decomposition is not unique. For example, if you consider one boundary, one loop, genus 1 case, there are lots of pants decomposition of the same surface. And of course, if this loop goes around very complicated way, then this L becomes very big. So very big L corresponds to very complicated winding. And so if you integrate this LS over to 0 to infinity, it of course diverges. And it includes all the modular, all these surfaces. And of course, what we should do is to integrate over the fundamental domain. So the correct definition is this one. But the fundamental domain is very complicated in general. And Mirzakhani proposed how to the way to calculate this integral. And let's talk about the, okay, G equal N equal 1 and the length of the boundary is 0 case. And McShane discovered the following identity. If you consider this function of the length L, and then if you add this F function, well, gamma L means the length of the curve, which is transformed by the modular transformation. The modular transformation changes the length of the curve. And if you add up this one over this modular group, this becomes 1. And Mirzakhani says that, okay, if you use this identity, then you can calculate this integral. And okay, if you multiply this, the left and right hand side by this one, then you get this equation. And this one is, of course, this volume we want to calculate. And the right hand side can be transformed like this. This measure is invariant under modular group. So you can rewrite this into this one. Then if you change the variables, then this integral can be given like this. And if you add this one, add up, okay, F is the fundamental domain. So if you sum all these one, then this becomes the whole region. L goes to 0 to infinity and the theta goes to 0 to 2 pi. Then you get this integral. And this integral can be done, and we have this one. This is what Mirzakhani shows. So using this kind of identity, you can calculate this volume. And what we should do, okay, if you want to calculate the general volume of MGN with GN general, then what you should do is to find out this Max-Chain generalization of this Max-Chain identity. And Mirzakhani find out the generalized Max-Chain identity like this. Here, okay, you consider genus G n boundary surface like this, and you fix one surface, and you also focus on one boundary whose length is L1. Then okay, and you consider the Pants decomposition of this surface. Then the pair of pants which has boundary with whose boundary includes this boundary. There are two patterns. One is like this, and one is like this. Okay, lots of patterns. Okay, LA is the other boundaries. So there are two kinds of patterns. And so you have, okay, in this case, you have two other boundaries, gamma and deltas. And actually, if you fix one surface, then there are infinitely many possibilities for gamma and delta. And they are actually related by modular transformation. And we also have, in this case, we have just one boundary, but there are infinitely many choices of this boundary. And they are also related by modular transformation. And so you add up all the possible gamma and delta. Okay, you add up this function, D, over all the possible gamma and delta for one surface. And also you add up t plus d over all the possible all the possible loop gamma choice of this surface. Then this add up to be L1. That's what Mirzakhani showed. Okay, so this is the generalization of the Max-Chain identity. And actually, this identity can be given for G equal 1, N equal 1 case by, okay, if you differentiate this one for G equal N equal 1 case over, differentiate with respect to L1 and take L1 goes to 0 limit, we get this Max-Chain identity. Okay, so we have generalized. Okay, we have generalized identity instead of this one. So what we should do is to multiply the identity by a integration measure and integrate over fundamental domain. And that's what Mirzakhani did. So this multiplying this identity by this one, and we get this recursion relation for the volume of the moduli space. And one can calculate this volume of moduli space by solving this equation, because the right-hand side is expressed by the volumes of the simpler moduli space compared to this one. So recursively, you can calculate all the, in principle, calculate all the volumes. Okay, so that's what Mirzakhani did. And what I would like to do, what I would like to show is that we can generalize this to a recursion relation for closed bosonic strings. And we get this equation. It's a bit complicated, but okay, the idea is very simple. Okay, in string theory, amplitudes are given by integrals over moduli space of Riemann surfaces. And the moduli space of Riemann surfaces are parameterized by this, the length. Okay, if you Pants decompose the surface, then you get the moduli space is parameterized by this L and theta. And so the amplitudes is, roughly speaking, given by this integral. So this is, okay, so this is just another integral over the moduli space, over the fundamental domain. So it is conceivable that we can derive a recursion relation for these quantities in the same way as we did for the recursion relation for this volume. So what we should do is the following. The idea is very simple. Okay, if you start from this generalized Max-Jane identity and multiply this measure and integrate over the fundamental domain, you can get recursion relation for this one. So instead, if you multiply this one by this measure, which involves correlation function on the worldsheet, then you get some recursion relation for the amplitude itself. This is what I have done. The idea is very simple, and the equation I get is this one. And so idea is very simple, but there are several details I should explain. For one thing, we should define the off-shell amplitudes. We are talking, okay, in the Mirzakhani business, they were talking about the Riemann surfaces with boundaries. And in string theory, we always talk about punctured Riemann surfaces. And there, okay, actually, if you start from a Riemann surface with, with hyperbolic surface with boundary, then there's a canonical way to make it into a punctured Riemann surfaces. You just attach to each boundary semi-infinite flat cylinder. And then you get the punctured Riemann surfaces. This operation is called grafting, and you get denote this grafted surface by this symbol. And so we have a punctured Riemann surface, so you can define the off-shell amplitudes for bosonic string theory in the usual way. Another thing I should mention is B-ghost insertions. Okay, we are taking here, we take the this LS and theta S, the length of the boundaries of the Pence decomposition and twist angle as the moduli parameter. So what you should do is to construct the B-ghost insertion corresponding to the tangent space, tangent vectors like this, like these. And they are constructed by following the standard prescription, like Sen's off-shell amplitude and superstring theory paper, or Harold's book. And according to them, these B-ghost insertions are expressed by variations of transition functions between local patches. And in our case, the local patches can be taken to be the pairs of pants. All the surfaces are decomposed into pairs of pants. And on the pairs of pants, it can be considered as like this. We dissect 3 disks from the complex plane, like this. And the complex plane has a obvious local coordinate z. So we use this z as the local coordinate. So this pants has a local coordinate, canonically defined local coordinate. And this pants itself is a hyperbolic surface, so you can graft it to be the punctured Riemann surface, you add up the semi-infinite, flat semi-infinite cylinders. And we take the coordinate of the semi-infinite cylinder to be W, like this.
So I have some questions.
Yeah.
So shell amplitude you're defining, it depends. Have you fixed the geodesic lengths on the boundaries, or are you just allowing them to vary?
But okay, I have fixed the external length of the external lines, right?
The lengths are fixed to some number one, or are they allowed
no.
from each other?
It can vary.
Okay.
Okay, if you fix it, but it can be anything, any combination.
Okay, so for the endpoint amplitude, it depends on n length parameters.
Yeah, right.
So does this amplitude, does it depend on the choice of Pant's decomposition?
The amplitude itself does not depend on the Pant's choice of Pant's decomposition.
How do you see this?
Okay, so okay. Anyway, this measure does not depend on the Pant's decomposition. And okay, and this combination does not depend on the Pant's decomposition. So this also does not depend on the Pant's decomposition. And so and also correlation function does not depend on the Pant's decomposition.
Okay.
I mean, one way to see it is that basically Pant's decomposition is putting markings on the geodesics, right? So that marking shouldn't change anything.
Okay.
Yeah, you say, okay, this is the geodesic. I mean, the amplitude doesn't change that.
Okay.
Right. Okay.
Yes, thank you.
So, okay. And so, okay, we have to describe the transition function of, for example, if there are two Pants adjacent to each other, then we should describe the transition function between these two coordinates. And this configuration can be considered as the limit of this one. We consider usual plumbing fixture. And so then, okay, so then we can see that if you follow the standard procedure, we can show that this ghosted insertion can be written like this. So if you change the length of this curve loop, then ghost insertion, there are two contributions, one from this Pants and one from this Pants, and each terms can be expressed by this function W, like this. And this function W are given in terms of hypergeometric function given by these people. And okay, so and B del theta is fortunately it's given by this integral over this loop. But the important thing is that B del L is there are two contributions from this Pants and this Pants. And so that makes the a bit of things complicated, because if you calculate the recursion relation, if you in deriving recursion relations, you have to factorize amplitudes. But your ghost insertion has to this form. So there, if you factorize this one, then there are two contributions like this.
Can I
So yeah,
just add
yeah.
something? Right. Isn't there some kind of incompatibility between the hyperbolic metric, Pan's decomposition, and the corresponding plumbing fixture that was, I think, pointed out by Musavian and Pierce that you cited earlier?
Incompatibility of what?
Yes, between the Pan's decomposition using a hyperbolic metric and a corresponding standard plumbing fixture.
Well, we don't actually use. You mean okay? Is there some?
That the gluing,
I don't know.
The gluing doesn't quite work at that transition point between the two surfaces, and there was some error associated to that they had to take into account somehow. And it turned out.
Okay. They were talking. Okay, they were talking about that. This plumbing fixture with a finite length. If you consider this one, then we don't have any incompatibility.
I think
Musavi and Pius tried to make try to use this cylinder with finite height.
I think the issue wasn't coming from that. Issue was coming from the fact that you're taking L equals to 0. And then
L equals okay, L equals 0. Okay. But
so the vertices of Musavian and Pius, they were not they didn't have geodesic boundaries, right? So these cubic vertices are different from the one we're working with. So that's why there's no problem.
Yeah, right. I think so. Yeah. Okay. So coming back to this one, you have these two contribution in the factorization. So actually, this means that you need two kinds of string fields to describe the recursion relation. And one is with this ghost insertion and one with no ghost insertion. So we should prepare this kind of two. Okay, so we need a doublet of string fields, which is labeled by index alpha, which takes value plus or minus. And so anyway, the string field is labeled by three things. I is for the states of the string Hilbert space, and the length of the boundary, and this index alpha, which takes plus and minus. And according to this alpha, okay, depending on this alpha, we should include this ghost insertion, which comes from this one. And so our string field or our amplitude, the external line of the amplitude is labeled by these three things, and I collectively denote this by a capital I. So the amplitude is given by this, and we get the recursion relation for this this amplitude like this. A bit complicated, but you can do that. Okay.
Sorry, can I just check? Aren't you gluing across geodesic boundaries, or are you doing something different? Aren't these boundaries all geodesic boundaries?
All the geodesic boundaries. So it's just you just identify them. Yes. By twisting. If there's a possibility of twisting.
Yeah. So then Ted made a comment before that because they were gluing along geodesic boundaries, that the problem appeared, but that you aren't using geodesic boundaries. I'm not sure what. Maybe he can elaborate a bit.
No, I said the opposite, that he was using geodesic and Musavian and Pius were not. So their cubic vertex was not, the boundaries of their cubic vertex were not somehow geodesics. They were not using pairs of pants. They were just using a 3-punctured hyperbolic sphere, and they were just kind of cutting off the punctures in some kind of arbitrary way. So when you glue it, then it's not, the boundaries were not geodesic for them. So
Okay. Thanks for that.
Okay.
Thanks for the comment.
Okay. So we get some recursion relation. It's a bit complicated, and what we should do is to construct a string field theory from it. So this is some recursion relation for the off-shell amplitudes. And one can derive amplitudes. As in the Mirzakhani recursion, we can also derive amplitudes perturbatively solving this equation, because right-hand side is expressed by less complicated things compared to the left-hand side. And this kind of equation can be considered as regarded as a Schrödinger-Dyson equation of string theory. So it is conceivable that we may be able to construct a string field theory from this equation. And actually, we had an experience in doing that. And this equation can be turned into an SFT in the Fokker-Planck formalism via the method developed by my colleagues. And the way it goes is given in this one slide. Okay, we have off-shell amplitudes. Okay, in the previous slides we were talking about connected amplitudes and at each order. So we put together everything, and we consider the off-shell amplitudes altogether. And formalism, this one should be expressed by this quantity. We should prepare these operators and the vacuum states. And what we should do is to construct this Fokker-Planck Hamiltonian. And here, for this off-shell amplitude, we have a recursion relation I just explained. And this recursion relation I explained is can be expressed by as this equation for the generating functional of this off-shell amplitudes. We put in source field, a source Ji. Then this functional differential operator with respect to J acting on this generating functional equals 0. And I should mention that in some previous in some slides ago, someone asked me the Virasoro constraints, algebra and Virasoro constraints. Okay, in the case of usual loop equation, this one satisfies Virasoro algebra. This is the Virasoro constraints. And in our case, this TI, this functional differential operator does not, I don't know for sure, but it does not seem to satisfy any closed algebra. But anyway, we can put.
Sorry, what do you say when you say that one operator satisfies is Virasoro? Well, like you have one operator. How is that giving you any Virasoro relation?
Okay, in the case, okay. In the case of the 2-3 critical point case, this T is a function. Okay, this becomes a T function of L, TL, length of the external line. And if you Laplace transform that TL, then you get the Virasoro. It is a function. Okay, it is just it's not just one operator. It is infinite. Okay, here in this case, infinitely many things here. I is denotes the infinitely many things. It is not just one operator, and this satisfies some algebra. Okay, in this case, we don't know if it satisfies some algebra, closed algebra, but in the case of a non-critical string, this satisfies some closed algebra. That's a Virasoro algebra.
Okay, but the question was kind of whether you have some sort of underlying conformal element. So in the story with vertex operator algebras, you know, your vertex operator algebra corresponds to the state. Well, it consists of the states in your theory, and in it you might have a conformal element. And if you apply the state to field if you apply the state field correspondence to this conformal element, you recover a field such that its coefficients are the Virasoro operators. Is that something that you can get here too?
I don't think so. In this case, we don't have any. Okay, first of all, in our case, we don't have any algebra yet. So we don't know if there's some symmetry or anything here in this case. In non-critical case, it's very simple. Things are very simple, were very simple. But in our case, I don't know. That's my answer.
Thank you.
Okay. Okay, so we have a recursion relation in this form. And on the other hand, on this side, if you, if this, we are talking about this one, and if this limit is possible, then we have this equation. And if you rewrite this one into an equation for a generating functional, in this formula, generating functional can be this is written like this. Then we get this equation, and this is something like a Schwinger-Dyson equation. And actually, you can derive this equation from the perturbation theory. You can perturbatively expand this one and calculate the correlation function. And from perturbation theory, you can derive this one. And okay, so in order to express this one by this one, then we have to have equivalence of these two equations. And there's a way to so we want to know what is the Hamiltonian, and Hamiltonian can be constructed by this formula. Okay, so if you take this one, if you take HFP to be like this, then of course this HFP is a linear combination of this TI. So if this equation is correct, then this follows. And moreover, if you can derive all the correlation function of this equation, that means the solution to this equation is kind of unique, at least perturbatively. So then if this one satisfies this equation, then these two should be the same. So you can derive from this this equation from this one, and if the solution is unique, if you know the solution is unique, then these two are equivalent. That's the logic of the deriving this formula. And so if you know the recursion relation, you can get the Fokker-Planck Hamiltonian. In the operator form, we have this one. So eventually, yeah.
Nobuyuki, so just to tell you that it's 2:15, so I think 10:15 for you. So just in case you need to catch your bus.
Oh, okay.
To make sure you see the time.
Yeah, okay, I'll be fast. Okay, so we have Fokker-Planck Hamiltonian eventually, and it is like this. Okay, all these non-hatted quantities are just C numbers. So we have, okay, if you look at this Hamiltonian, you get only kinetic terms and the 3-string interaction terms. And you can prove from this, following the logic in the previous slide, you can get this equation. So we have the Fokker-Planck Hamiltonian, Fokker-Planck formalism for the string field strings. And in the conventional field theory case, we had an action S. And Fokker-Planck formalism is just a rewriting of the usual formalism. And in our case, we also can consider this action formally. It is defined. This Boltzmann weight can be given by this quantity in the Fokker-Planck formalism. You can show this by okay. This is how you can show this equation. And from this expression, you can calculate S at least perturbatively. You can, from this equation, you can derive the equation for S by the Schwinger-Dyson equation like this. And if you solve this one perturbatively, you can get this one. So this action, okay, so it is, I think it includes infinitely many terms. And the first two terms are this kinetic term and the 3-string vertex. And there's one tadpole term and other infinitely many terms. And schematically, I've written the action here. The first two terms, actually, these are the Dohoga-Gross action. And this one tadpole term, this is actually, okay, I've written this, but this is actually divergent. And if you formally, it can be given like this. So first of all, this action is ill-defined. And this tadpole term actually do the following thing. If you calculate the one loop, 1 point amplitude, then from Dohoga-Gross action, you get this one. But this term, tadpole term, gives this contribution. And this is just a formal manipulation. And if you add up, then you get the correct answer. So it seems that this action has the infinitely many counter terms. And so the action S is not so well defined, but Fokker-Planck formalism is well defined. The difference is the following. Fokker-Planck formalism, for example, for one loop, 1 point function, there are infinitely many terms. But in the Fokker-Planck formalism, they are assigned some weight following according to the Mirzakhani scheme, and they add up to be this one. So that means these configurations related by modular transformations contribute different quantity to the amplitude. So that means this Fokker-Planck formalism breaks the modular invariance.
Sorry, are you saying that the tadpole term is cancelling the infinity from the modular group?
Yes, right. That's what happened. Okay. So we have the Fokker-Planck formalism, but it's not modular invariant. Actually, you can see that it is not invariant of the BRST transformation on the worldsheet. Of course, we need worldsheet BRST symmetry to define physical states with positive norm. And in order to discuss this symmetry, we changed the notation to the usual SFT way. You take the first quantized Hilbert space as the string field to be an element of first quantized Hilbert space. And Hamiltonian is given like this, and the BRST transformation is given like this. And this is not BRST invariant because, as I said, that this formalism is not modular invariant. And if it is BRST invariant, it should be maybe modular invariant. So as actually, if you calculate the BRST transformation of this Hamiltonian, you get this quantity, and this is does not vanish. Here, if we express this one by that t, which comes from the recursion relation and pi, like this, and then you get this form. And this is not invariant, but amplitudes are invariant because the things which appear here, P and Q is given by this, are actually null quantities satisfying this one. So if you consider this correlation function, then these quantities does not contribute. So even this is not zero, but they are actually null in a sense like this. So using this fact, we can modify the Hamiltonian by adding these terms with some auxiliary field. And by adding this, but these are, as I said, these are null quantities. So by adding these, that does not change the amplitudes. And also, if you add this one, then you can take the BRST variation of these auxiliary fields, so that this modified Hamiltonian is invariant. And we had to add this auxiliary field. And if adding auxiliary field, it's more appropriate to express the form everything in terms of path integral formalism. So we made the action like this. And this action is BRST invariant, and it consists of actual kinetic terms and the three-string interaction terms. Okay, so we have got this formalism action, and this is made of kinetic terms and three-string interaction terms and BRST invariant. Okay, that's what I've done, and I don't know. Okay, there are several problems, many problems left, and one of them is that we are talking about BRST transformation on the worldsheet, but we don't know how to interpret it in the second quantized language. And also we have to, okay, we were talking about bosonic string, closed bosonic strings, but I would like to make it into superstrings. And that's what I'm working on right now. Okay, that's what I have to say, all what I have to say. Thank you very much.
Thanks a lot. So I will stop recording, and